Hello, my name is Sanin Haveric. I'm from University of Sarajevo, Institute for Genetic Engineering and Biotechnology. I will lead you through the Module 4 of this course, and this presentation is about exposure pathways to depleted uranium. Uranium is a heavy metal that is chemically toxic and radiologically toxic since all its isotopes are radioactive. Uranium is an emitter of high-energy alpha particles. Other industrial activities, like those requiring the use of phosphate fertilizers, with which uranium forms strong complexes, and the use of coal-fired power plants where uranium concentrates in the ash, are also likely to cause pollution and environmental dispersion. The health risk associated with small particles of uranium incorporated into the body raises concern, whereas uranium toxicity is relatively well documented in situations of acute exposure at high doses. It is much less so in situations of chronic exposure at low doses. Among the endogenous and exogenous factors that can modulate uranium toxicity, the age of the individual is known to influence the rate of intestinal absorption of uranium, 20 to 100 times higher in newborns than in adults, and the epigenetic sensitivity of the individuals during the embryonic and fetal periods of development, the delayed effects of which can affect the individual in adulthood or even its progeny. Sex can also modulate the renal excretion rate of uranium and thus its toxicokinetics. Preclinically, this rate is higher in males than in females. Genetic polymorphism also has an influence on uranium toxicity. Uranium accumulates mainly in the kidneys and bones and can cause kidney disease and cancer. The beta and gamma emissions from depleted uranium contribute to an external radiation dose, primarily affecting the skin. External exposure to depleted uranium typically occurs during combat situations, when depleted uranium aerosols are generated or when depleted uranium fragments are handled. For larger depleted uranium fragments, the contact dose is approximately 2 millisievert per hour, while dust particles result in much lower exposure. Soldiers in vehicles with depleted uranium armor experience prolonged external exposure, though at very low dose rates around 1 microsievert per hour. Internal exposure to depleted uranium can occur through ingestion, inhalation, and embedded fragments of contaminated wounds. Ingestion may take place via contaminated food and water, while inhalation can occur through aerosols generated during combat activities. Embedded fragments and wounds, which are primarily concerned for soldiers, can also lead to significant internal depleted uranium exposure. Ingestion of depleted uranium is not considered the major exposure pathway. However, direct ingestion is an issue among children through hand contamination in populations such as in Iraq that use metal from battlefield to produce cutlery. Direct ingestion of contaminated soil by cattle and sheep as a pathway to humans has also to be considered. Since the contaminated areas are generally small, it can be assumed that food contamination will be negligible. Uptake of uranium with drinking water is one of the major ways of incorporation of natural uranium. Contamination of drinking water with depleted uranium can be caused by depleted uranium dust, fragments, or penetrators buried in soil. Inhalation of dust is considered the major pathway to depleted uranium exposure. There are two possible ways of generating depleted uranium aerosols. The first is the impact of penetrators on hard surfaces, and the second one is the fire, as depleted uranium is highly pyrophoric. When depleted uranium munitions strike their target, a cloud of depleted uranium particles ranging from 0.2 to 15 microns in diameter is produced. The quantity of aerosol formed during impact depends largely on the hardness of the target. Aerosol formation is also enhanced if the penetrator breaks up and melts. Particles formed inside the vehicle either adhere to the inside surfaces or are released into the atmosphere through any opening. As they accumulate on interior surfaces, the particle size and mass may change due to agglomeration processes. Particle size vary greatly, from larger, easily visible fragments to very fine, respirable particles that can reach the lower parts of the lung. The aerosols generated at impact may lead to considerable inhalation exposure. Embedded fragments of depleted uranium ammunition that cannot be removed surgically can result in chronic internal exposure. When inhaled, dust particles are either trapped in the oropharynx, where they are eventually swallowed, or they reach the lower airways, where they are subject to alveolar absorption. This absorption occurs in two phases. Firstly, early rapid phase happens, which results in peak plasma concentrations and levels, and then there is a decline followed by a prolonged period of steady absorption. About 95% of inhaled particles greater than 10 micrometers aerodynamic equivalent diameter deposit in the upper respiratory tract. Particles below 10 micrometers can reach deeper pulmonary regions and deposit for considerable time. Inhaled depleted uranium appears to have a pulmonary half-life of about 4 years. The amount of depleted uranium that is absorbed into the blood and deposited in tissue and organs depends mainly on particle size and the solubility of the uranium-containing particle. This solubility determines how quickly and efficiently the body absorbs uranium from the lung. Soluble chemical forms are absorbed within days, while insoluble forms generally take months to years. Toxic chemical effects are more likely to be associated with the more soluble forms of uranium, while radiation effects are more likely to be associated with the insoluble forms, such as particles that are deposited in the lung and local lymph nodes and retained for extended periods of time. In blood, approximately 47% of the uranium forms a complex with bicarbonate, 32% binds to plasma proteins, and 20% binds to erythrocytes. Up to 90% of dissolved uranium reaching the blood compartment is excreted within the first few days after a single exposure. The remaining 10% deposits in bones, kidneys, and other organs, from where it is mobilized over a longer period of time. The kidneys are the critical region and organs for uranium chemotoxicity. Bones act as a depot for the metal, and once environmental uranium exposure has stopped, it will be released from the bone for months or years to come. Elimination is principally through the urine, making the kidney particularly vulnerable to damage from uranium, and high levels of uranium accumulate in renal tissue. At higher doses of uranium, kidney damage is the major threat to patient health and survival. However, recent work has shown that chronic low-dose depleted uranium exposure, specifically 20 months in rats, can produce subtle pathologic changes in the kidney along with blood chemistry changes related to renal dysfunction. Depleted uranium is able to cross the blood-brain barrier and tends to accumulate in certain brain regions more than others. Specifically, following oral exposure, the hippocampus and striatum show higher accumulation of depleted uranium compared to cerebellum and cortex. However, with dust exposure, depleted uranium accumulates in the central nervous system, in the olfactory bulb, hippocampus, cortex, and cerebellum, in that order of increasing concentration. Large dose acute exposure to uranium would probably be the result of an industrial or laboratory accident. Regardless of the form, if large doses are ingested or inhaled, acute renal failure due to tubular necrosis is the result. Treatment of uranium intoxication involves removal of the source of exposure and supportive treatment. The LD50 of uranium for humans has been calculated to be about 14 mg per kilogram, depending on the chemical form. Chronic exposure to low doses chemotoxicity is predominantly for chronic exposure to uranium as a heavy metal. Uranium, like other heavy metals, can be considered as a mitochondrial toxin and can induce mitochondrial dysfunction in different target organs. The chronic ingestion of uranium in drinking water altered the expression of xenobiotic metabolism-related enzymes involved in detoxification. Thank you for your attention.